In our series on carbohydrates, we have discussed monosaccharides extensively. In my last lecture, I had discussed glycosides with you, and we know that a monosaccharide, that is hemiacetal structure of monosaccharide, reacts with a molecule of alcohol in acidic medium to form an acetal. And the acetal of monosaccharide is known as glycoside. During the glycoside formation, a glycosidic linkage is formed, which is a ether linkage. So today, in today's discussion, we shall be using our information to see how disaccharides are formed, and for that matter, what are disaccharides. Disaccharides are made up of two units of monosaccharides linked by a glycosidic linkage. So when I talk of a glycoside, what we've seen, that a hemiacetal form of glucose reacts with an alcohol in acidic medium to give us a glycoside. Now we are going to do the reaction between two molecules of monosaccharides, in which one molecule is going to act like a simple sugar, and the second molecule of monosaccharide will act like a simple alcohol. And reaction takes place between the anomeric OH of the sugar part and any one of the hydroxyl groups of the second sugar, which is the A-glycan. So what happens here is a bond formation takes place between the C1 and the C4, resulting in the formation of a glycoside. And a glycosidic bond is formed between C1 carbon of the first monosaccharide, which is acting as a sugar part, and C4 carbon of the second sugar, which is acting as an alcohol. So what do we see? That the anomeric OH reacts with the OH on the fourth carbon to form a glycosidic bond, and this linkage is known as 1,4 linkage. So that means, what are disaccharides? Disaccharides have the molecular formula C12H22O11. These are sugars which are composed of two monosaccharide units which are joined by a carbon-oxygen-carbon linkage, which is known as the glycosidic linkage. This linkage is formed, as I've already discussed, by the reaction of an aromatic carbon on one cyclic monosaccharide with the OH group of the second one, and in this case the second monosaccharide is acting as a simple alcoholic group. So that means when we are forming disaccharides, one sugar molecule is acting like a glycan, and the other molecule, which is simply acting like a simple alcohol molecule, is the A-glycan part of the glycoside. So when we talk of the formation of the disaccharides, what we find is that the OH group, which is attached to the anomeric carbon, will react with the OH group of the other monosaccharide. Why does the anomeric hydroxyl group take part in the reaction? This I have discussed in my last lecture, that in this case the oxocarbenium ion which is formed is most stable, since it is stabilized by resonance. So what we find here is that the monosaccharide here, this one which is acting here as the sugar molecule or the glycan part, the hydrogen from here as proton reacts with the OH of the alcoholic group of the second monosaccharide, which is acting as an alcohol, and a water molecule is eliminated, resulting in the formation of a disaccharide along with a water molecule. And we call this as a condensation reaction, because two molecules of monosaccharide are reacting to give us one disaccharide and a simple molecule, that is water. That is, water is eliminated in this reaction. And if we do the reverse of this reaction, That is, we do the hydrolysis of disaccharide. What I mean by saying we do the hydrolysis of disaccharide, that is, we break the glycosidic linkage with the help of water, then we will get the monosaccharides back. And this is what normally happens, that when we take in food, like if we are taking in sucrose, it undergoes hydrolysis in small intestine, and there it is the enzymatic hydrolysis, that is the enzyme saccharase breaks down sucrose into glucose and fructose, which are then absorbed by the body, by the bloodstream. So now, if I talk further of disaccharide, then what we find is that the monosaccharide units may be same as in case of maltose. Maltose is made up of 2 molecules of D-glucose, whereas if I talk of sucrose, then there the 2 monosaccharide units are different. That is, one is D-glucose and the other is the fructose unit. So that means the disaccharides may be made up of only one type of sugar, or they may be made from 2 different monosaccharides. And then the next point that you have to remember, we'll be discussing this in detail again and again, that the anomeric carbon of one monosaccharide may react with any of the hydroxyl groups of the another monosaccharide unit to form a disaccharide. So when this linkage takes place, how can these linkages take place? There are 3 possibilities. One possibility is that there is a bond formation, is the 1,4 link. What I mean by saying is 1,4 link is that the anomeric carbon of the one monosaccharide unit reacts with the 4th hydroxyl group, that is the hydroxyl group on the C4 of the second monosaccharide. And the example for this will be maltose, which we will be discussing. Then we can have 1,6 link, and when we talk of a 1,6 link, then what we find is that in this case the anomeric carbon of one monosaccharide is bonded to the oxygen on the C6 of the second monosaccharide. And then the third type of linkage that we can have is the 1,2 link. 1,2 linkage means that the anomeric carbon of both the monosaccharides are involved. That is, both of the monosaccharides are bonded through an anomeric oxygen. So in this case, both of the monosaccharides will act like a glycon as well as a aglycon. Now what we find is, now after talking of the linkages, we have to see how can these 2 sugars be joined when they are involved in when the O-glycosidic bond is formed. So what we find is that these sugars can be bonded in 2 ways. In one way, what we have is, I am showing it to you, we have this moiety. This moiety is acting as a glycon. That is the hemiacetal OH or hemiacetal carbon is involved in acetyl formation by reaction with the hydroxy group of the other monosaccharide. And in this case, we can take any of the hydroxyl groups of the second monosaccharide, and this monosaccharide is acting like a aglycon. This is the aglycon part and this is the glycon part. So the hemiacetal carbon or hemiacetal OH of glycon is involved in bond formation, resulting in the formation of a glycosidic bond here, a glycoside. And what we find is that in the aglycon part, the hemiacetal carbon is free. That is, it is not involved in glycoside bond formation. So when we will dissolve this particular disaccharide in water, it will undergo mutarotation. That is, it will convert itself into the open chain structure, and hence it is a reducing sugar. So when it forms into an open chain structure, that means the aldehydic group is free, and since the aldehydic group is free, it will act as a reducing agent. That is, it can react with Tollin's reagent and Felling's and Benedict solution. The other case may be, okay, Now what we find is that if we do the acid hydrolysis of this disaccharide, please remember disaccharides are stable in aqueous medium and in basic medium. So if we have to do hydrolysis, we'll have to do acid hydrolysis of this disaccharide. And when we do the acid hydrolysis of this disaccharide, what we find is that we will get the monosaccharide units, which is the sugar part, as well as the other monosaccharide, which is acting like a glycon part. Now the two sugars can also link in a different manner. So how is this disaccharide, which I have shown on the screen, is different from the disaccharide which we've just discussed? What we find in this case is that both the sugars here, both the monosaccharides, are acting here as G. Like this is acting, in this case, this is acting as a glycon, and this G dash will act as an aglycon. Whereas if I talk of this as a glycon, then this part is the aglycon for this disaccharide. Reason being, what happens in this case is that the bond formation is taking place between the two anomeric OH. That is, this anomeric OH of this monosaccharide is formed in bond formation in the glycoside formation, as well as this is involved in the glycoside formation. So what we find is neither of the hemiacetal groups is exposed. Hence this sugar is a non-reducing sugar. That is, it will not give us test with Tollens reagent, Felling's reagent or Benedict's reagent. But nevertheless, we can carry out the hydrolysis again in the acidic medium, and when we carry out the hydrolysis in acidic medium, what we find is it will break down into its monosaccharides, and when it does so, what we find is it will regenerate, or it will regenerate the hemiacetal carbons, and we will get the reducing sugars. But this will happen only if we bring about the acid hydrolysis. So what we've done here is we've broken down the disaccharide into its monosaccharide units. Whereas if we have taken the disaccharide as such and we do the Tollens test or the Felling's test, it would give us a negative test. Once we've done the acid hydrolysis, it will break down into its monomer units or the monosaccharides, and then these monosaccharides will give the Tollens test or the Felling's test. So now I shall be discussing important disaccharides, which are maltose, cellulose, lactose and sucrose. So before I proceed further, let me take in detail the formation of maltose. So if I talk of maltose, then what we find here is that the alpha D glucose, the reaction here is between the alpha D glucose and the beta D glucose. So what we are talking here is, this is the beta D glucose, but what we find here is that this OH is acting simply as an alcohol. So now when I talk that the bond will be formed between this anomeric carbon, and this anomeric carbon belongs to alpha D glucose, hence the glycoside which will be formed or the disaccharide which will be formed, we will call it as alpha D, because which carbon is being involved? The anomeric carbon here is being involved, which is the alpha D glucose. Now the reaction takes place between this carbon, which is at number 1, and the carbon at number 4. 1, 2, 3, 4, and we are getting a number 4, and a water molecule is eliminating here, resulting in the formation of maltose molecule. Now if we look into the example before I proceed further, so what we see is, like if I talk of glucose, whether it is alpha D glucose or beta D glucose, the molecular formula is C6H12O6. Whereas when I talk of a maltose, which is an example of a disaccharide, what we find here is that the molecular formula will be C12H22O11. So that means during the formation of a disaccharide, from monosaccharide a water molecule is being eliminated? Since water molecule is being eliminated, this is a condensation reaction. If water molecule was not being eliminated, the molecular formula would have been C12H24O12, which is not the case. So that means this is a condensation reaction. So alpha is indicating what? Alpha is indicating the configuration around the glycosidic bond, that is here. And then the second thing that we have to keep in mind is, one is indicating the position of the anomeric carbon, and it is forming a bond with the OH at the fourth carbon. So here we've indicated that the carbon number 1 of one monosaccharide, that which is involving the anomeric carbon, is reacting with the hydroxyl group on the fourth carbon here, resulting in the formation of a glycosidic linkage, that is maltose. And how do we name this? Since this is the coming from here, this is the glycoside or this is the acetyl. So what we say is this is alpha. Here we are representing the configuration around the anomeric carbon. Then this has D configuration when we talk of the open chain structure, and this is glucopyranosyl since this is the acetyl. And then the linkage is between 1 and 4, which we simply say alpha 1,4, and this is the glucopyranose, that is the hemiacetyl part of the structure. And now since OH is exposed here, so when this will act as a reducing sugar. So that means maltose is made up of 2 molecules of glucose which are linked through alpha linkage. Now if I talk of 3 important disaccharides which are maltose, lactose and sucrose, then what we find is that in case of maltose, alpha D-glucose reacts with D-glucose, resulting in formation of maltose plus water. So that means the glycosidic bond here, now we have to remember this, is between alpha, that is the configuration at the anomeric carbon is alpha, and the C1 carbon is linked to C4 carbon of the second monosaccharide, which is acting as an alcohol by a glycosidic linkage through ether linkage, that is through O. Whereas if we talk of lactose, then lactose is beta D-galactose. So that means what, when we are writing alpha here, beta here, I'll just take these 2 cases. What I mean here is that the configuration around the anomeric carbon in glycon is alpha, and in case of maltose, whereas when we talk of lactose, then the configuration is beta, and beta D-galactose reacts with D-glucose, resulting in the formation of lactose and water. So what you have to keep in mind is that when we are stressing, we have to stress on the configuration at the anomeric carbon, that is at the glycon part. Whereas a glycon part, we can just write it like D-glucose, because any of the OH of the a glycon part can react with the anomeric carbon of the glycon part to give us a disaccharide. Now if I talk of sucrose, now sucrose is a different case. So when I say sucrose is a different case, what we find in sucrose is that the anomeric carbon of glucose, which is C1, and the anomeric carbon on fructose, which is C2, are involved in glycosidic bond formation. So in this case, what we have is, we have to now, that means indicate the configuration around both the anomeric carbons. So in case of glucose, it is alpha, whereas in case of fructose, it is beta. So this we've indicated by writing alpha, beta, 1, 2. So that means alpha carbon, that is alpha carbon of the hydroxyl group, alpha, where the configuration is alpha in glucose, and the configuration at fructose is the beta. And we are going to get, the linkage is going to be between the first carbon and the second carbon, and both these carbons are anomeric carbons. So I'll quickly now revise what do I mean by saying alpha and beta. So this, when we talk of maltose, what do we mean by maltose? Where do we get maltose from? Maltose is also known as malt sugar, and what we find is beer is rich in maltose. The sugar present in beer is maltose, and maltose is also present in grains. It is also present in wheat, and it is also present in wheat sugar, and it forms the fiber part of the carbohydrate. It is the present in the fiber part of the carbohydrate, like it is present in the fruits, it is present in maize, it is present in wheat, it is present, and it is used as a sugar substitute. So when we talk of maltose, what I have shown here is the glycosidic linkage, and when we talk of a glycosidic linkage, here we've shown the alpha D linkage, alpha linkage here. So when we are showing the alpha linkage, we will point this towards the lower side. The bond, oxygen bond, the ether bond will be shown towards the lower side, and this is the glycosidic bond. This glycosidic bond is between the first carbon, that is of the glycon, and the fourth carbon of the aglycon part. That is, the linkage is between the first carbon of one monosaccharide and between the fourth carbon, which is acting like a simple alcohol to form alpha D maltose. So when I say that this is having alpha configuration, so what I mean here is that the CH2OH and OH are on the opposite side, then we say this is the alpha configuration. Whereas if OH is on the same side as CH2OH, then we say the configuration at the anomeric carbon is the beta carbon, is the beta configuration. So I have already shown that we have a glycosidic bond here. So what happens is that in sprouted barley seeds, we do the hydrolysis of the starch present in sprouted barley seeds, and this hydrolysis is carried out with the help of enzyme diastase, and this diastase brings about hydrolysis here, which breaks down this maltose into its monomer units or into its monosaccharide units, which are alpha D glucose. I think in one of my previous series I had shown alpha D and beta D, but maltose is made up of only alpha D glucose and not of alpha D glucose, and the alcohol part is also the alpha D glucose. Now when we eat maltose, what happens in our system? In small intestine, enzyme maltase is present, and this enzyme maltase hydrolyzes maltose to give 2 D-alpha glucopyranose molecules, that is 2 molecules of glucose, which are then absorbed in the small intestine. So if we look here, so what we find is that the OH of this first carbon, the anomeric carbon, and the OH at the fourth carbon here take part in the glycosidic bond formation. A water molecule is eliminated here. So what we say here is that this is a condensation reaction. 2 monosaccharides are reacting in acidic medium to give us maltose, which is in which the glycosidic linkage is between the first carbon and the fourth carbon. So what we have to remember further is that if we talk of maltase, maltase is a specific, we know enzymes are specific in nature. That is, they will cleave only at a specific site, which is the active site of the substrate. So maltase does not hydrolyze beta glycosides. So which certainly shows that maltose has alpha glycosidic linkage and not beta glycosidic linkage. And the aglycon unit will exist as a hemiacetal. This we've seen in a last reaction also. That is, how does this unit here is hemiacetal unit, this here, this is free here with. So what we talk here is that this is free. So now what we have is That is, this maltose will now act as a reducing sugar because it has a hemiacetal unit. So when we will dissolve maltose in water, it will undergo ring opening. And since it undergoes ring opening, it will also show mutarotation. Now what we've seen that when we talk of maltose, the glycosidic bond is specified as alpha 1,4 and is simply stated as alpha 1,4. So when we talk of this alpha 1,4, what we mean here is that the configuration around the anomeric carbon which is involved in bond formation is alpha. But in the other case, if we see, if the OH group had been in the beta configuration when the glycosidic bond was formed, the bond would be in beta 1,4 configuration. So that means we've changed the configuration around the anomeric carbon, and when we do so, what we'll get is we'll get a different molecule altogether, which is cellobiose. And cellobiose would have different two-dimensional and three-dimensional shape when compared to maltose, and its physical its properties would also be different. So what I mean here is, like, if I am talking of maltose here, so what we find in case of maltose, here the linkage is alpha, that is the linkage is between alpha 1,4 glycosidic linkages here, right? So the configuration around this carbon is going to be alpha. Whereas when we talk of cellobiose, then what we find is that in cellobiose, the configuration around this carbon is going to be beta, right? And when the configuration here is beta, what we find is that the linkage is different, and since the linkage is different, that cellobiose will be a diastereomer of maltose. Although both are made up of glucose, the only difference is that they are differing in configuration at the anomeric carbon. Here the linkage is alpha 1,4, whereas in this case the linkage is beta 1,4 glycosidic linkage. So now, as I've already said, that cellobiose is a beta glycoside and it is a diastereomer of maltose. It differs in configuration only at the anomeric carbon of the glycosidic linkage, and then it has 1,4, that is beta 1,4 glycosidic linkage, as contrast to alpha 1,4 glycosidic linkage in maltose. So this is the structure of cellobiose. So how is this cellobiose obtained, or from where it is obtained? Cellobiose is present in very small amounts in cellulose, and it is formed by partial hydrolysis of cellulose by the enzyme cellulase present in the microbes. And it is the enzyme emulsion which hydrolyzes the B glycosidic linkage of cellobiose to yield only glucose units. And since cellobiose contains a free hemiacetal group, so it is a reducing sugar, it will undergo mutarotation in aqueous solution, and it will exist in equilibrium mixture of the three forms, that is the alpha form, the beta form, aldehydo form. That is in all the three forms, the alpha form, the beta form and the open chain form, and it will also be able to form oximes or ozozones, which are the characteristic reactions of a free aldehydic group. So now if we talk of another very important disaccharide, then we talk of lactose. And lactose is known as milk sugar because it is present in milk of mammals. And then what we know is that lactose is made up of D-galactose and D-glucose. In this case, D-glucose unit is present in the beta form, that is the, and we say that is the I can say that the subunits are beta D-galactose and alpha D-glucose. And in this case, now the galactose unit is the one which is involved in an acetal formation, that is we get a glycosidic linkage here, and the glucose part, in the glucose part is acting like an alcohol, simple alcohol, and in this case the hemiacetal it exists as a hemiacetal. So what we find here is that in lactose, galactose is linked to glucose, and the first carbon, that is the anomeric carbon, where the configuration is beta, is linked to the fourth carbon of the glucose molecule through the ether linkage. And since it has a free aldehydic, or it is a hemiacetal, so hence lactose is going to be a reducing sugar. So what I have again shown here is that we have 1,4 bond here, and this linkage is a beta linkage, and the anomeric carbon is free here, hence it is going to act like a reducing sugar. And what we find is milk, cheese, curd, all these compounds or all these products are rich in lactose. So if we talk of the formation of lactose here, so what we've seen here is that the beta form here, beta form of galactose, what is the beta form? In which the OH and the CH2OH are on the same side of the ring. This reacts with the OH on the fourth carbon of alpha D glucose, and a water molecule is lost here, resulting in the formation of a beta glycosidic linkage. Again here, this is a condensation reaction. Now what we know is that this is digested, lactose is digested by enzyme lactase to form glucose and galactose in the small intestine. So what happens is that when we talk of this here, enzyme brings about hydrolysis at this place. We can even bring about acetic hydrolysis. And what we find here is that this molecule breaks down to give us D-galactose and D-glucose. Now, sometimes what we find is that some people are not able to digest lactose. That is, they're allergic to lactose. That means they're allergic to milk. So we say that this allergy is due to lactose intolerance. That is, in some individuals, enzyme lactase is inactive and it does not break down this lactose into galactose and glucose, as a result of which what happens is that lactose accumulates in the colon and gets fermented to generate carbon dioxide, hydrogen, methane and irritating organic acids. And these compounds will cause abdominal pain. It may even cause bloating, diarrhea and vomiting. And this is due to what? Lactose intolerance. That is, the enzyme lactase is not active in the small intestine and it does not break down lactose to galactose and glucose, as a result of which what happens is that lactose accumulates in the small intestine and there it undergoes fermentation to give us methane, hydrogen, carbon dioxide and noxious acids, which will then cause the cramps, that is the stomach ache and vomiting and diarrhea. Another important disaccharide is a sucrose. Sucrose is also known as invert sugar. It is also known as table sugar and it is the most abundant disaccharide. It occurs in photosynthetic plants, and please remember, sucrose is sweeter than the other disaccharides, that is maltose and lactose. And in this case now the molecule of sucrose is different, because in this the glycosidic linkage is between the anomeric carbons of the D-glucose and D-fructose. So what we know here is that this is the anomeric carbon of D-glucose and this is the anomeric carbon of D-fructose. So what happens is that both the anomeric carbons are involved in bond formation here. So what we have is, this is the alpha form here. Now let us look into the structure here. So this is the alpha, because in this case the OH here is on the opposite side of CH2OH. So the configuration around this anomeric carbon, which is the anomeric carbon of glucose, is alpha. And when we talk of the fructose moiety, then what we find here is that in this case CH2OH and the OH are on the opposite side. Since they are on the same side. Since they are on the same side, the configuration here will be beta. And since the configuration here is beta, that is, they are here on the same side, so the configuration here is beta. So that means if the linkage, we are referring to linkage, here we will say it is a beta linkage in case of fructose. So both of them are acting here as glycon as well as aglycon. That is, for glucose, aglycon is fructose, and for fructose, aglycon is glucose molecule. And the glycosidic linkage is between alpha C1 of glucose and beta C2 of fructose. So this is what I have shown here, the formation of the glycosidic linkage, which is occurring between, this is the C1. Here the numbering is wrong, it should be C1, C2, and this is the C2, C3, C4, C5 and C6. So what we find here is that this OH and this OH are on the same side. So here the configuration is going to be beta, whereas in this case the CH2OH and OH are on the anomeric OH are on the opposite side. So the configuration here is alpha. So this is a linkage which is known as alpha 1 here because of the anomeric carbon 1 of glucose, and beta 2 because of the anomeric carbon 2 of fructose is involved in bond formation, and this linkage is known as alpha 1 beta 2 glycosidic linkage. Whereas when we were talking of maltose, we were saying it was alpha 1 2. For cellobiose it was alpha 1 4. For cellobiose it was beta 1 4. So please, you have to remember this, that when we talk of the alpha and the beta, we are talking of the configuration around the anomeric carbon. And since in sucrose both the anomeric carbons are involved in bond formation, we will refer to both the linkages, that is alpha 1 beta 2 glycosidic linkage. So this is what again I have shown here in this slide again, that this is the glucose here, this is the fructose and the beta glycosidic bond formation. So in this case it is beta here and it is alpha in this case. So now when we talk of sucrose, what we've seen it, that both the monosaccharide units in sucrose are present as acetals or glycosides. That means it does not have a hemiacetal group. Since it does not have a hemiacetal group, since both the anomeric carbons are involved in acetal formation, sucrose is a non-reducing sugar. That is, it will not show mutarotation and it will not be easily oxidized. So it is not a reducing sugar. So because it does not undergo mutarotation and it does not undergo oxidation easily, so what we find is that this property of sucrose finds vast use for preserving foods like jams and jellies. And the other important thing that you have to remember is that sucrose is the major sugar for translocation within the plants. So now what I referred in the beginning, that sucrose is also known as invert sugar. Why is sucrose called as invert sugar? It is not that sucrose is invert sugar. It is because when we do acid hydrolysis of sucrose or enzymatic hydrolysis of sucrose, it yields 1:1 mixture of D-glucose and D-fructose. Now we know that the specific value or specific rotation of sucrose is 66.5, that is positive, and the resulting mixture of glucose and fructose has a specific rotation of minus 22. So what we find here is that when we bring about hydrolysis of sucrose, there is change in rotation. That is, the sign of rotation changes from plus to minus. So since the sign of rotation of 1:1 mixture changes, we call this 1:1 mixture is called as a invert sugar. So that means mixture of glucose and fructose is known as invert sugar. Now we know that honey, which is the most common, it is the most common form of invert sugar. Why so? Because honey bees have invertase enzyme in them which breaks down sucrose into glucose and fructose. And that means honey is rich in sucrose, and the enzyme will break it into honey is a mixture of glucose and fructose. It is because the enzyme will break down sucrose. Now what we find is that since sucrose on hydrolysis is giving us glucose and fructose, so honey is sweeter than sucrose because glucose and fructose are sweeter than sucrose if we look into the sweetness index of the sugars. So what we find is not only this, the enzyme saccharase, which is present in the small intestine, will hydrolyze this sucrose into glucose and fructose, and the glucose and fructose are absorbed in the intestine because the disaccharide sucrose has a large size, so it cannot be absorbed as such. It cannot be absorbed into the bloodstream. So sucrose is broken down in small intestine into glucose and fructose, which are then absorbed by the bloodstream in small intestine. Now, I had talked in the beginning, I've been saying again and again that sucrose is a non-reducing sugar because it does not have a hemiacetal group, free hemiacetal group. Whereas if we talk of maltose, lactose, they are reducing sugars. So what is the reason? What are non-reducing sugars and what are non-reducing sugars? So we say that like acetals, glycosides are stable with basic reagents and in basic solutions, and they may be reducing or they are non-reducing. Why are they non-reducing? Because the hemiacetal part of them is involved in bond formation when I talk of methyl glycoside. But if I talk of lactose, then in that case, since the hemiacetal carbon will be free, it will be a reducing sugar. So we say that acetals, glycosides are stable with basic reagents and they are non-reducing. They are non-reducing because they are not in equilibrium with their open chain carbonyl forms in neutral or basic aqueous solutions. Hence, they cannot be oxidized by tolerance reagents. So for non-reducing sugar, so what we say like acetyl glycosides are stable. So when I talk of an acetyl, what I meant by saying acetyl is that when a monosaccharide reacts with a methanol or ethanol in presence of acid, it gives us an acetyl. And that is stable because the glycosidic bond is formed there. That is, we are converting hemiacetal into an acetyl. So hemiacetal is not available there for reduction. That is, it will not undergo ring opening. Whereas if I talk of glucose, then that's a reducing sugar because when we dissolve glucose in water, it undergoes ring opening and that means glucose is a hemiacetal. It has a potential aldehyde group. Whereas in simple language, if I say acetyl does not have a potential hemiacetal group. So why are they non-reducing? Because they are not in equilibrium with their open chain carbonyl forms in neutral or basic aqueous solutions, and hence they cannot be oxidized by tolerance reagents. And you have to remember that glycosides are acetals which do not mutarotate. That is, if I talk of methyl O glycoside, glucopyranose, it will not mutarotate because it is the acetal form. So what I mean here is, this is what I have taken here, which I have been trying to tell you for quite some time now. That is, we have a acetal form, acetal formation has taken place here. And since the acetal formation has taken place here, we do not have a potential aldehyde group. Since we do not, and we know this is stable, this linkage is stable in basic medium as well as in aqueous medium, so it does not give us reaction with tolerance reagent. Like if I talk of this, so this is what I have been talking, that if I talk of beta D glucopyranoside, or if I talk of ethyl alpha D glucopyranoside, because here the ring is 5 membered, that is, it is a furan ring, so they will not undergo ring opening, they are stable in basic medium, and hence they are non-reducing sugars. So I'll be discussing this in my later lecture also, that sucrose is also a non-reducing sugar. Please remember, we do not have a free aldehyde group there. And what we find is, when we talk of a starch or a cellulose, or when we talk of a polysaccharide also, that will also be a non-reducing sugar. Why? Because we do not have a hemiacetal group in them. So what are reducing sugars? Reducing sugars are hemiacetals or hemiketals, which are in equilibrium with the open chain sugars in aqueous solution, and they will reduce tolerance reagent. So what I mean here is that if I take beta D glucose, I dissolve beta D glucose in water, it will undergo ring opening. When it undergoes ring opening, the aldehyde group will be free, and when this aldehyde group is free, although the amount here is very small, as we've discussed in the case of mutarotation, that is, the beta form is 64%, alpha is 36%, and this is just 0.02%. This will react with tolerance reagent and it will give us silver test. And this aldehyde group will be oxidized to a carboxylic group. So another important thing that you have to keep in mind is that tolerance reagent does not only distinguish, it distinguishes between glycosides and hemiacetal form of the sugar, but it cannot distinguish between aldoses and ketoses. This again I have discussed in detail in one of my previous lectures, that a ketone under basic condition undergoes a inidiol rearrangement, and when this inidiol rearrangement takes place, what happens is the furanose structure of the ketone opens up to form a open chain structure, and then there the ketose isomerizes to give us an aldehyde. That is what is happening here, is that is, we are getting an inidiol intermediate here from a ketone, and then this is when it will give us a aldose. Isomerizes to give us an aldose, and this aldose on reaction with tolerance reagent will give us a positive test. That is, we know that when we heat aldehyde with ammonical silver nitrate, or when we heat glucose with ammonical silver nitrate, which is tolerance reagent, we get a beautiful silver mirror at the bottom of the boiling tube. So from this, as I've already discussed in the beginning, that if the anomeric carbon is, one of the anomeric carbon here is free, like in this case, in case of maltose, cellobiose and lactose. So these sugars are reducing sugars, that is, they'll give us positive tolerance test, positive Felling's test, they will form ozazone. But if we talk, and they will also show the phenomena of mutarotation. Whereas when we talk of sucrose, then what we find is that both the anomeric carbons are involved in bond formation, that is, it has no free aldehyde group. Hence, it is a non-reducing sugar, that is, it will not mutarotate, it will not give us Felling's test, and it will also not form ozazone derivatives. So this is what I've shown here, that sugars having free aldehyde groups are reducing. For example, glucose, fructose, lactose, maltose, these are all reducing sugars. Whereas if we talk of glycosides like methyl glucoside and sucrose, they are non-reducing sugars and they do not mutarotate, as we find here that the linkage here is formed between the acetyl, between the anomeric carbons. So both the anomeric carbons are involved in acetyl formation. So I hope you learned something here, and we will be continuing with further with reducing and non-reducing sugars in my next lecture, as well as polysaccharides, and we shall also take up some derivatives of carbohydrates in the next lecture. Thank you.